哦，没有，这个首先是上面。What?
Can people in the back hear me? Great. Okay, so today we're going to talk about, we're going to finish our lecture about thermodynamics, hopefully. Then that will just give us some flexibility in terms of our course, because we are ahead of schedule. So before I go ahead, I just want to do a survey that we're gonna have at least one lecture. We can arrange the content pretty flexibly. So what do you want to do in these lectures? I'm just gonna read out each option. So we're gonna vote, right? So after I read out each option, you can just raise your hands. So I'll do a count so I can gauge people's opinion about this. Okay. Yeah, for those of you who are late, we're gonna do a survey to decide. We're gonna have some flexibility in terms of 1 or 2 lectures. So we'll decide what to do for those 1 or 2 lectures. Option 1, we can continue with next topic in our syllabus, right? Those of you who favor option A, please raise your hand. Okay.
Yeah.
Some good. Option 2, we're gonna discuss some homework problems of your concern.
There you go. That one.
What's that? Well, it depends, right? We can do another survey, right? We can discuss previous homeworks. We can also discuss future homework, right? If that's helpful. Then option 3, you can discuss some exam problems.
That's the feature.
Well, obviously that's going to be previous, right? Past exam. It's not going to be future exam.
I'll keep your mind.
Then option D is like open. I'm open for suggestion if you have.
Like any numerical examples in class that can relate the derivations to the physical world.
Okay.
Like we've gone over a lot of derivations and I understand how to derive equations, but I don't know like what they.
Okay. Well, then that would be the homework. Okay. What else? Okay, good. Seems like we need to spend some time discuss homework as well as exams. So we will have our first exam graded most likely, over this weekend. So we will have all the grades ready in our next lecture. So I will share that with you. And I mean, before I announce the kind of statistics of the exam, each of you should be able to see your own grade in the Canvas, right? And then I post the statistics, then you should be able to really access how well you're doing in this course in a relative sense, compared to your peers, compared to the median, the 20, 40, 60, 80 percentile, and the maximum and minimum. And I think the exam, when I design the exam, I know the homework problems are hard because you have plenty of time to do it, right? And you can work in teams, and it's designed to really help you to spend time thinking about the problems, applying the knowledge. But when it comes to exams, the whole goal is to examine if you understand these concepts and if you can use it. Right? So, and I understand that in the exam you have a short time, and a lot of people are not doing very well in exams because they panic. So I'm trying to make the difficulty, make it less difficult compared to the exams, compared to homework. So if you are able to do the homeworks without any problem, right? Or even without problem, after you discuss with your peers, you are able to successfully understand the exams, get it done. Then you should have the confidence to do the exam. Okay. So that's kind of my philosophy about exams, and that's for most of the exam problems that will be kind of the difficulty level. So in that regard, and for next exam, I will probably just post some previous exams, right? I will probably discuss those exam problems just to help you to prepare. And then I guess we're gonna, after we kind of like give out the exam grades, we will see what first do a survey, obviously, because we cannot, probably it's not a good use of our time to discuss every exam problem, but we will discuss those problems you guys have the most concerns. Regarding homework problems, yeah, we think I think we also need to do the survey, right? So I will do some preparation, next lecture, and then so I'm just gonna list a list of homework problems. We're gonna do this survey first, then we will just go over the homework problems that have the most concerns first. Okay. Any problems? Any questions? No? Good. Then we can continue. So today we're going to continue to talk about the free thermodynamics and the phase equilibrium. In last lecture, we briefly talked about the difference between states and the rate, and we re-emphasize that equilibrium is about, thermodynamics is about equilibrium, and equilibrium is the kind of the branch of chemical engineering that really deal with the states of the systems, and then whether the system is in one state or another really depends on the energy of the system, and how fast our system can move from one state to another depends on the transport and the reaction rate, right? That are required to supply the chemical species for the reactions, when do our system? How do we know our system is in equilibrium, right? For a multi-phase, to answer this question, we need to look at the free energy of the system first. So in chemical engineering, because in thermodynamics, you probably learn about several different free energy, free energies, right? Including the Helmholtz free energy, the Gibbs free energy, and so forth. But in chemical engineering, most of our systems we study our system under constant pressure and temperature. So in that scenario, Gibbs free energy is the most frequently used free energy. And for a system that has six different species, the free energy is a function of the temperature, the pressure, as well as the moles of each species in this system. Okay, and then phase equilibrium means the energy of the system does not change anymore, right? Otherwise, and we know for a system, simultaneously the energy will go downhill, right? Which is the energy will decrease until it reaches a minimum, and that's when our system reaches equilibrium. So mathematically, the condition for phase equilibrium is dg over, the derivative of g equals 0, right? That's where mathematically you find out the minimum point. So phase equilibrium is achieved when g is minimized. Then for a C component system, the dg, the differential of the free energy, is a function of minus sdt plus vdp plus this term. Then this is partial g over partial n at when pt and j are fixed, multiplied by dni, right? This is like dni is the change of moles of species I, and we sum this over all the species in the system. So here S is entropy, and it's partial entropy, and mathematically it's equivalent to partial G over partial T, when pressure and the N are fixed. And V is volume, it's part, and mathematically it's partial G over partial P when temperature and Ni are fixed. Okay. So here partial G and partial N at constant PT when PT and J are fixed has another name. It's called chemical potential. Okay. This is a thermodynamic property, and the physical meaning of chemical potential is how much the energy of the system change when you add 1 mole of species I into your system while making sure all the other parameters are not changing, right? Making sure pressure, temperature, and Nj are not changing. Okay, so this is a dg for a system that has 6 different species. Now, if we are dealing with a multiple phase, like a closed system with multiple phases, then total free energy is going to be the free energy. We add up the free energy of each phase, right? From phase 1, let's say if we're dealing with a system that has n different phases, then the total free energy is going to be the free energy of each phase. Here we use the superscript in parentheses P to refer P's phase, right? The free energy of the P's phase, and you add it up together from P1 to N. That's a total free energy. Then dg is going to be the summation of the dg of each phase. Okay. So now, at constant temperature and pressure, and we know these 2 terms just vanished, right? Because at constant temperature and pressure, dt is 0, dp is 0. Then we have only this term, right? Then the free energy change of the system will be basically, first, if you look at each phase, then we need to add up the free energy of each component multiplied by how much this component has changed, how much the moles of this component has changed, right? That will give you the free energy change in the P's phase. Then you just add it up across the n different phases. That will give you the total free energy change of this multi-phase system. Okay. If our system is non-reactant system, that means the total amount of moles are conserved, because if there are no reactions, then you don't generate or you don't consume number of moles. So the number of moles is conserved. Mathematically, that is to say, if you add D and I, like species I, across all the different n phases, it's 0, right? Net change is 0. And if we rearrange this equation, we take out the number of moles change of species I in phase 1. We take it out, we single it out. It's going to be equal to the minus the summation of the change of other, the species I in other phases, right? From phase 2 to phase N. Okay. So questions so far? Okay. Yes.
So the only thing that changes in a multiple phase system is the internal energy term. Is that correct? Like the other 2 terms with change in temperature, change in pressure are just the same as normal. Is that true?
So like here we assume temperature and pressure are fixed. Then that can help us to simplify this equation.
Okay.
Okay. Because if temperature is fixed, is constant, then dt is 0, right? This term is 0. Pressure is fixed, and dp is 0, right? Then the free energy change of the system will only depend on the chemical potential of your species I, as well as the number, the change of moles of species I. Okay. So here the whole point of doing this is that we want to derive the phase equilibrium condition, right? Because at a system level, we know when your free energy is minimized or dg is 0, your system reaches equilibrium. But in a lot of cases, we don't know about the total free energy of the system. We don't want to know, right? We don't care about the total free energy of the system. What we care about is the energy of each component, right? Which is the chemical potential. We care about the chemical potential of each species in each phase. Here we are trying to derive the phase equilibrium condition. Now, when you have this, right, if you plug in this into this equation, that will give you this. So this may takes a little bit derivation, but I'm going to show you how to do this. So I mean, start from this, right? Now we have two summation here where we sum over all the components, I mean, in each phase, and we also sum over the sum through all the phases. Now, if for DG system, right, DG, so for DG system, right, so I'm just gonna write S here to denote system. We can take out the phase 1. Okay. This is going to be a constant T P, right? Plus so this is the the okay. So mathematically, we just kind of break down this whole summation into two terms, where we single out phase 1, right, here, and the rest of all the rest other phases, right, mathematically. Then we know, because this equation here, you can plug it here, dni1 equals this whole term. So this term can be rewritten as then now you will have basically so this is going to minus okay. So if you plug in dni1 here, that will transform this term into this functional form, where you have basically summation over from species 1 to species C, and summation from phase 2 to phase N, right? And in each then you have mu I in phase 1 multiplied by dnip, right? Then you just now there are these two terms will have many similar properties. Then now you just put them together, then you will have mu ip minus mu I1, right? So mu ip minus mu I1, with this. That's how it's derived. Now, what I want to say here is, here, even though we do single out phase 1, you can also single out phase 2 or phase 3 or phase N, right? This can be done for any phase, which is to say, this equation here, this mu I1 can be mu I, 2 or 3, right? But correspondingly, you have to change this as well. If you have phase 1 single out, then now you sum from phase 2 to phase N. If you have here, you have phase 2 single out, then here you sum over phase 1, phase 3 through N. Okay. So why this is important? We will see this in the next slide. Okay, now we get this equation. As you can see that now we have the differential of the system free energy equals to the summation of many of these kind of like a difference, right? And as we just showed, this difference, this one can be any phase, right? That is to say, this is kind of somewhat arbitrary. So in order for now you have a parameter, which is a summation of many, many difference. And in order for this parameter to be zero, then each of your difference needs to be zero, right? So that just helps us to derive the condition for phase equilibrium, right? When this equation is zero, that means the mu I in phase one equals mu I in phase P, right? And if you generalize this to all the phases, that is to say, at phase equilibrium, the chemical potential of any species should be equal in all phases, right? Mu I in phase one equals mu I in phase two, and equals mu I in phase n, right? Yes.
Couldn't you have one term be positive and the term be negative of the same magnitude, and they wouldn't have equal zero, the terms cancel out?
Yeah, that's possible if you only do phase one here, right? So you can if you only single out phase one, then you can still have -1 plus +1 will give you zero. But now we're talking about this difference is arbitrary. It's actually the difference between any two phases, right? Because mathematically you can do that. Now, in this case, you cannot, there's only one way you can make this term to go to zero, which is every difference is zero, right? So mathematically, you can prove this. Kind of the real power is arbitrary, right? This difference is arbitrary, right? And in order for this difference, and then in order for the summation of so many differences to be zero, then each difference needs to be zero, okay? Now, in addition to the chemical potential of any species needs to be the same across all phases, we also need to have the temperature across all the phases needs to be the same. Otherwise, if there's a temperature difference between phase one and phase two, then we know there will be heat transfer happening, right? Then your system is not at equilibrium, because we know equilibrium means there's no macroscopic change. Similarly, pressure in each phase needs to be the same. Otherwise, you will have momentum transfer. Right? If you between two phases, pressure are not the same, you will have momentum transfer, then you will have fluid flow. Okay. Now, the problem with chemical potential, right? There's a limitation with chemical potential is that when we are dealing with gas phase mixtures, when your gas phase goes to a vacuum, that is to say the pressure goes to zero, or approximates zero, then chemical potential goes to -infinity, right? Mathematically, we really do not like infinity because it just makes all the math operations difficult. So that's why chemical engineers define this concept called partial fugacity, which is correlated to the chemical potential by this exponential equation. So here, RT is really used to scale mu I, so that this whole term becomes unitless, right? And the partial fugacity have the unit of pressure. So C is a temperature dependent constant, and it has a unit of, it has the same unit as pressure. Now, as we can see, this equation is monotonic equation, right? That means, when Fi increases, mu increases. When Fi decreases, mu decreases. That is to say, then we can convert the phase equilibrium condition from that the chemical potential of species I in all phases need to be same to the fugacity of any species in all phases is equal. Okay. So for pure component, partial fugacity becomes pure component fugacity Fi. For pure ideal gas, fugacity equals the total pressure, and for component in an ideal gas mixture, partial fugacity equals its partial pressure. Okay, so we'll see this in the table here. So this table, it's from your textbook, and it gives this basically summarize some of the important thermodynamic quantities for phase equilibrium. You know, at first glance, it may look very complex, but if you spend some time look through it, you will find out it's not that difficult. So we start from chemical potential, which we just talked about. It's by definition, it's partial G over partial N. The physical meaning is the free energy change of your system when you add 1 mole of component I into your system with all the other parameters fixed. Okay. And for ideal gaseous solution, this mu I is equals partial molar free energy. Then we just define the partial fugacity to be exponentially dependent on mu I. So when mu I goes to minus infinity, right? That's when pressure goes to 0. Then Fi goes to 0, right? That's a benefit of defined fugacity. And for ideal gas and solution, partial fugacity in the vapor phase is proportional to the mole fraction of your species I in the vapor phase multiplied by the pressure. Partial fugacity of your species I in the liquid phase is proportional to the mole fraction multiplied by the vapor pressure. Okay. Now we also define fugacity coefficient of a fugacity coefficient, which is basically we kind of normalize partial fugacity with some pressure, right? Because we just talked about partial fugacity, and as it says here, it's like thermodynamic pressure. It has the unit of pressure, and sometimes it's convenient for us to normalize this partial fugacity into like a unitless kind of a quantity. That is when we can we define fugacity coefficient to be the ratio of fugacity divided by pressure. Okay, and then for a mixture, the partial fugacity here in the vapor phase is a partial fugacity divided by YIP, right? That's again a pressure, but that's kind of the partial pressure of species I in the vapor phase. And in the liquid phase, we can do the same here. Then activity is further a relative thermodynamic pressure in which we basically, kind of like normalize your partial fugacity with a standard fugacity Fi0. So that will give you again a unitless quantity. Okay, then activity coefficient is basically you normalize your activity with your mole fraction. Okay. So I mean, these kind of relationships made it so you don't have to remember it, but just go back after lecture, go back to read it and try to understand their inherent relationship, and it's kind of straightforward. And I mean, right now it may seem like why we do define so many different quantities, why bother do such complex things, but the reason for doing this is like as later on you will find out some of these definitions will greatly help us to simplify our problem. Okay. Now, so we have explained that at phase equilibrium, the chemical potential of any species I needs to be the same throughout all the phases, and in the table we show in this slide, we defined partial fugacity, we defined activity, right? Now you see, we'll do this step by step, right? Partial fugacity is dependent on the chemical potential in a monotonic function. Then activity is only a ratio of your partial fugacity, normalized by a reference point, right? So that is to say that in order for mu I to be equal across all phases, then Fi bar needs to be the same and AI needs to be the same as well, right? So that is to say, at phase equilibrium, the chemical potential, fugacity, and activity of any species is equal in all phases, right? But this does not apply to activity coefficient or fugacity coefficient, right? Because if you come back, no. The fugacity coefficient is defined, with respect to a pressure, right? This, when mu I is equal, that doesn't mean, so when Fi is equal, when Fi in two phases are equal, that doesn't mean phi, which is fugacity coefficient, will be equal, right? Because the pressure in these two phases are not necessarily the same, right? The same goes to activity coefficient. So this should be quite straightforward if you look at the mathematic functional form. Now, that really give us some convenience, right? Now, if we to look at phase equilibrium to say how do we correlate phase equilibrium condition to something more tangible, and we relate the phase equilibrium condition to the mole fraction of species I in each phase. To do that, if we look at this definition here, this is like a partial fugacity of species I in the liquid phase, right? From the table in last slide, it can be written as this or this. Similarly, the partial fugacity of species I in the vapor phase can be written as this or this. Okay. Now, at equilibrium, we know if we are talking about a liquid vapor phase equilibrium, in which let's say we have such a container. We have liquid phase here, we have vapor phase here, right? We have many different species, species I, J, and etc. in both the liquid phase and the vapor phase. We use Xi to denote the mole fraction of each species in the liquid phase. We use Yi to denote the mole fraction of each species in the vapor phase, right? Now, for a given, for a chosen species, for example, species I, at equilibrium, we know the chemical potential of species I in the liquid and vapor phase is the same. And we also know the partial fugacity of species I in the liquid and vapor phase is the same, right? That is to say, this term equals this term, or this term equals this term, right? Or this term equals that term, right? So there are kind of four terms. So there are four combinations in total. But let's say if we only look at these two combinations here, right? If we set them to be zero, to be equal, and if you rearrange this equation, you will find out Yi over Xi, right, equals the fugacity coefficient L divided by the fugacity coefficient in the vapor phase. Okay, that is to set these two equal, and you compare these two. Similarly, you can get this, right, which is basically by set this equal to this, and you can get this by set this equal to this. Okay, and rearrange the terms. Okay, now we'll use this on the next slide. So here, from the phase equilibrium condition, we can derive that the mole fraction of species, mole fraction of ratio of species I in the vapor and the liquid phase equals this ratio. Okay, and this ratio and this ratio. Now this quantity, right, this ratio of mole fraction of species I in the vapor and liquid phase is called K value, right? And the physical meaning of this is that K value tells us how much, for a liquid vapor phase equilibrium, K value tells us how much species I wants to stay in the vapor phase compared to the liquid phase, right? Because we just talked about in this case, we have the liquid vapor equilibrium. And this is your system. We have a species I, J in both kind of phases. Species I may want to, come out from the liquid phase and enter the vapor phase, or the reverse, right? At equilibrium, yi and xi is not necessarily the same, right? Actually, seldom it's the same. It's always not the same, right? So if this key value here is very large, right? Much larger than 1, let's see. That means yi is much larger than xi, right? That means at equilibrium, you will have much more species I in the vapor phase in the liquid phase, right? In other words, species I really wants to stay in the vapor phase. It doesn't want to stay in the liquid phase, right? And we can define another quantity that's called relative volatility. That is the ratio of the key value of species I over species J, right? And it tells us kind of in a relative sense how much does species I wants to stay in the vapor phase compared to species J. Okay. So these are the quantity we define for a liquid vapor phase equilibrium. Now there could also be cases where we have a liquid, if we have two immiscible liquids, then we have a liquid equilibrium. We can define a similar quantity that's called Kd. That is the mole fraction of species I in liquid phase 1 and the mole fraction of species I in liquid phase 2. That's called the partition coefficient, right? It tells us how much does species I want to stay in the liquid phase 1 relative to liquid phase 2. And similarly, we can define a relative selectivity quantity. That's the ratio of this partition coefficient of species I over partition coefficient of species J. Okay. Now the Aij can really tell us, the value of Aij can really tell us, and for liquid vapor phase separation, the value of Aij can really tell us that how difficult or how easy it is to separate two species, species I and J. If Aij approaches 0, that is to say Aki equals Kj approaches 0, right? Then that is to say Ki, this is capital keys, Ki is much smaller than Kj, right? Then we have, Yi, Xi much smaller than Yj, Xj. Right? So if we start from a liquid phase in which Xi equals Xj, right? This is just assumption, right? Then this will give us Yi is much smaller than Yj. Yeah. So now you can see, if we start from a liquid mixture made of species I and J, now we try to create vapor from them, right? We put them into a tank and we start to create vacuum. Then both species I and J will evaporate and create a vapor phase. At equilibrium, in the vapor phase, amount of species I, the mole fraction of species I, will be much, much smaller than the mole fraction of J in the vapor phase. Right? Now we successfully basically separate the mixture of species I and J, right? By creating a vacuum, by creating a vapor phase from the liquid phase, right? Because we know in the liquid phase, the mole fraction are kind of close. I mean, in this case, in this assumption, they are equal. But in the vapor phase, there's almost no species I in the vapor phase, right? That's how we can separate it. Similarly, I mean, if you can do this here, right? The answer will be just the opposite. If you do this, then you will have yi, much larger than yj. In this case, if aij approaches infinity, then we will be able to, separate species I from species j. Okay. So, that's kind of go back to the definition of relative volatility, right? That's kind of the physical meaning of relative volatility. If the relative volatility of species I over j is large, very large, or very small, then they have very different volatility, right? Then we can separate them by vaporize them. But if their relative volatility is close to 1, they have very similar volatility, then it's going to be very hard or even impossible for us to separate them by creating a vapor from the liquid mixture. Okay. So we will use this key value when we discuss the distillation process. Okay. Okay. Guess I can stop here. We have some few slides we will talk about next week.
Yes, it was 4 slides. This is what I got. Yeah. Yeah, he said. General biology. I like it. Like your class. Great.
Yes.
I just want to be able to keep all of this straight right here. Can you tell me what N stands for?
N is the number of phases in a multi-phase system. And C is the number of components in one phase. Yeah, in each phase.
Little p.
So little p just refers to this is the chemical potential of species I in phase P.
Okay, so if we define liquid as P, then this would be the chemical potential of the species in the liquid phase.
Yes.
Versus the chemical potential in the phase, whatever phase.
Yes. For example, we talk about the binary system. I mean, two-phase system, not binary system, liquid vapor equilibrium. Then in that case, P will be 2.
Okay.
Then you have P1, that's liquid, and P2, that's vapor.
So it's just the difference in chemical potential between the two phases.
Yes, this is like, I mean, taking our example here, this will be the chemical potential of species I, the difference between the liquid and the vapor phase.
Okay, and this is just like as you change the number of moles.
This is basically the the change of moles of species I in phase P.
Okay, so this is number of phases. This N is moles.
Yeah.
Okay.
Yeah. That's kind of confusing. Yeah. But
Okay.
these two are different. That's number of phases.
Okay.
This is the number of moles.
Okay.
I said I'm trying to be consistent with the nomenclature in the textbook,
Yeah.
but I guess there are still some like a kind of a conflicting nomenclature in the textbook.
No worries, but that clears it up. Thank you.
the.